Good day, everyone. Welcome to our World Zen and Engineering channel. And in today's topic, we will be discussing the principles of geodesy. Now, this all has to do with pretty much understanding maps, and I'm sure as well engineers, you will agree with me that that's a very strong prerequisite for designing wells and executing them. I'm sure there's no, you have to know where you're going to be drilling the well. You have to know the exact location where you will be executing the well from the planning stage all the way to the well delivery and operation stage. So before we move ahead, please do not forget to like, do not forget to go to our channel, do not forget to like, do not forget to subscribe, do not forget to make your comments as required. So moving ahead, the outline of our presentation will be introducing the topic, we'll be looking at coordinate systems, then we'll be talking about datum, looking at the types of coordinate systems and which are the global, Cartesian or geocentric coordinate systems. We're talking about the geographic or geodetic systems. Then we're looking at the very important one, which we use as drilling engineers, which is the projected coordinate systems. Then we're talking about map projections, talking about types of map projections. Then we'll be zoning in into the very important one. That's the universal transverse Mercator. And so I'll be zoning in on the Nigerian projection systems. So, quick introduction. It is very important to look at this. Let's take a quick look at this quote. Every map user and maker should have a basic understanding of projections, no matter how much computer seems to have automated the process. Yes, that's very true because you look at a lot of drill engineers when they look at their drilling programs, they see map projections, they see UTM, they see the UTM system, they see UTM 82, they see they see the Nigerian projection system, they see the Mina datum. So there's a lot of this data that has been used or rather given to us to use to plan these worlds, but most of us don't actually understand where this is from. We hear the word datum. We don't even Most of us don't even understand what datum is being referenced when they give you some of these projections. Yes, longitude and latitude we understand. I mean, all that has been taught to us while we were in school, in secondary school. But having moved ahead, now that we actually use this information, we've gone past that. We need to understand how or where data on a flat surface, and that's where the projected data comes in. So we need to know how this geographic data has been projected on a flat surface. Because so quickly introducing geodesy. It's actually the science concerned with determining the size and shape of the earth. So what are types of geodesy that we have? We have the physical geodesy, which details the earth's gravity field. We have the geometric geodesy concerned with determining the positional relationships. We have the dynamic geodesy, which is concerned with the time variation of the point positions on the Earth's surface. And we have finally the satellite geodesy. Now, with all the new kind of technology we have, it is concerned with the positional relationship with by means of artificial satellites. So we're using satellites pretty much to tell us the position, the relationship with regards to different positions. For the purpose of our discussion, we'll be zoning in on geometric geodesy. So before we move ahead, just to make this a little bit interesting, we have a couple of data here, and I would like us to look at this data, have it in our minds, and try to differentiate it. We will be speaking about them at the end of this presentation. So let's look at it, pay very strong attention, and try to see if we can differentiate them. They are pretty much information that we have come across, I think, various times in from the from. I mean, we pretty much got this information from our subsurface team, from the geology team, and we have actually used some of this information to plan our worlds. But it would be nice that we look at it and try to see if we can differentiate them. So let's talk about reference surfaces so that let's build up to this topic. Talking about reference surfaces, we're looking at the geoid and ellipsoid, and I'd like us to understand it. Now, geoid is actually what the Earth is. That is this shape, the shape to the right. But I'm sure most of us think that the Earth looks like this. So what we think it is, what we think the Earth is, the ellipsoid, and what the Earth actually is the geoid. And what it actually uses, what why the shape of the Earth is like this, is looking at valleys, is looking is looking at hills, valleys, and even with using the world's mean sea level, you will still have a shape relative to the geoid. Now, what we try to do with the ellipsoid, we try to kind of make the shape of the earth uniform so that we can use it to do to project. We can, so that we can have a planar system, so we can use it to project. You all agree with me that if you want to use the geoid to project on the plane surface, it's actually going to be very, very difficult because of the irregular surface that it has. But with the ellipsoid that we've tried to ensure that we've constructed a uniform system, it will be very, very easy for us to project on any surface. So let's have that in our minds as we move ahead. So this is what we have now. Another very important topic to talk about is the datum. Now, for you to measure anything, you need to have a reference, and in this case, in geodesy, it's actually the datum. So the datum defines the position of the spheroid relative to the center of the earth. So say you looking at the far right, say you have this geoid, that's this irregular surface, and this is the center of the earth. So if you want to, say for example, measure from here to here, this is your datum. If you want to measure it on the horizontal, using the, if you want to measure the horizontal datum, this is going to be your reference. Now, what they've done, looking at it at the right, they've tried to make a planar surface out of it, and they've made it very regular. And that way, you see that it's very easy to measure. The red line here is an European datum, I think created in 1950, and this is the center. That's the red dotted lines. The black one is the North American datum created in 1927, and as you can see here, this is pretty much the center. So it serves as a reference or base for calculating the geographic coordinates of a location. So because you need to know what you are measuring against. That's pretty much what the datum helps us do. So further moving ahead, we have vertical components and we have horizontal components. As the name implies, the vertical component you're going to be measuring against the vertical. For the horizontal components, you'll be measuring against the horizontal. So you have, I mean, all both of them actually reference positions. So for vertical datums, you have different types. You have the North American vertical datum created in 1988. That's what you see in some documents as the NAD 88. You have the National Geodetic Vertical Datum of 1929, what you see in some documents as NGV D29, and so on and so forth. Then you have very, very important ones like the World Geodetic System of 1984, ellipsoid. So what it means is that it's referencing the ellipsoid. So you have WGS 84E, and you also have the World Geodetic System of 1984. So this references the geoid. And note, all these are vertical components. Again, WGS 84E references the ellipsoid, and WGS 84G references the geoid, and they are both vertical components. To the right, you have something down here that looks like what we've seen here for the geoid and ellipsoid, which is the World Geodetic System of 1984, also created in 1984, but this time it is called the WGS 84. So very easy to note that when you are referencing the geoid or the ellipsoid, it is a vertical component. But when you don't have pretty much any reference, you just clearly know that it's the horizontal component. So, moving straight into the meat of the matter, we're delving deep now. There are rather three types of coordinate systems. You have the global Cartesian, or what you might call the geocentric. It references the X, Y, and Z, or rather uses the X, Y, and Z. Then you have the geographic or geodetic coordinates, which I'm sure a lot of us know about. That's the longitude and latitude. And also there you hear them called the equator, you hear them called the prime meridian. Then you have the projected coordinates. Now, this is them using the geographic coordinates and projected onto a flat surface. But before that has to be done, it has to be put into a particular system before you make those projections. And in this case, either a cylinder, either a cone, or projected on a flat surface. So we'll see. I mean, we'll see a couple of them as we move ahead. So just moving, delving deep into these types of of systems, we have the global Cartesian. Like I said, it references the x, y, and z, and then where z is the actual height of the equatorial plane. Then the OX axis goes through the Greenwich meridian. The OXY plane goes through the equatorial plane, and the OXYZ looks at the directional the direct orthogonal reference. So this system pretty much uses the x, y, and z as points of reference. Then you have the next one is the geographic or geodetic coordinate. Now, the reference system uses the longitude and latitude. Like I said, a lot of us know about these systems and the way they are named. Rather, when you see the values that come from them, is either they use decimal degrees or they use degrees, minutes, and seconds. Now, now this is what the system looks like. Like all of us know, you have a longitude, you have your latitude, you have your equator, and you have your prime meridian. The drawback for this system is that it's not very good for making planimetric measurements. So, say I tell you I'm at a particular position on a flat surface. If you try to use the longitude and latitude to come and locate me on that flat surface, it is going to be very difficult. So it's always efficient to use the next system which we are going into now to locate someone on a particular flat surface. And that system is the projected coordinate. So it's a map projection. Rather, a map projection is a systematic transformation of locations on the Earth, that's the longitude and latitude, to flat surfaces. So um, clearly, what you can see here, you can see the projection being done either from a cylinder or cone or a flat surface. So what is done is that you take these systems, you put them into you take the geographic system, it's placed in a container, either of these containers that you used to that is used to project. So these are different types of projection methods. For the cylindrical, we have either the tangent, is either projected in the tangent method, secant, oblique, or transverse. Now, this is dependent on how the cylinder is placed, and we'll see it as we go ahead. For the conic, and these are different types: Arden close, Bermans, Cassini, etc., etc. And somewhere here you have the Mercator, which we're going to be zoning in when we're talking about the transverse Mercator. Then for the conic system, it's either tangent, secant, oblique, or transverse. And for the planar systems, you have the polar, equatorial, oblique, mnemonic, stereographic, and orthographic. And under here, you have different types or different ways which we've tried to do planar projections. So moving straight into the cylindrical projections, this is defining it straight in with this one line, with this one sentence. You just project a sphere onto a cylinder, like we see here. And there are different methods, like we said, it's either normal, transverse, or oblique. So the advantage which you have in green, or the positive, is that it's good for displaying the world, but more accurate in regions close to the equator. The regions close to equator are regions close to the center. So when you look here, what we're trying to say is that when you look here, sorry, let me get on my pointer option. So when you look here, you see that areas that have been projected towards the equator have almost equal lines. But when we go towards the pole sections, they are not evenly spaced like we have towards the center here. So that's what they're trying to tell us, that when you project upon a cylinder, you have equal spacing. It's kind of equal, but when you go towards the pole section, north and south pole, they are not equally spaced. That's what they are telling us. Right? So longitude lines are vertical and equally spaced, but latitude lines are horizontally and unequally spaced. That's around the pole section. So that's pretty much about cylindrical projection systems. So moving to the next one, that's the conic projection system. Straight one sentence, we project the sphere upon a cone. So it is good for displaying mid latitude areas, and that's what they're trying to show us here. So if you look at these mid latitude areas, they come out very even. And two methods that there are two methods that we need to highlight is either regular or it's placed in an oblique angle and used for some reasons so that we can get some areas and try to get them uniform. So this is the second type of projection system. Then finally, we have the planar or azimuthal projection system, where you are projecting the sphere upon a plane. So you have a plane here placed on top of the sphere, and you are trying to project everything in that region towards the plane surface. So up here we have different systems. You have the different methods. You have the gnomonic, you have the stereographic, you have the orthographic. So you see, we are taking different sections of the sphere and we are trying to project them towards the flat plane. For the gnomonic, you see it does it from like the center of the sphere. Here it does it from the pole section, and from this side it takes it from all the sides of the system and does it in an orthographic method, or rather in an orthographic matter and manner. But for the different methods, you see, they for the polar method, they've placed it above the sphere, projecting towards the polar regions. Then for the equatorial, it's been placed to the side, and we have the sections projected. We have the sphere projected to the side. Then for the oblique, the plane system has been kept at an oblique angle, and everything is projected towards that direction. So zoning into the very popular universal transverse mercator, that's UTM. I can bet you that there's no drilling engineer or subsurface person who hasn't heard this. And how that is done is that it's a cylindrical system, and it's widely used. So what's done is that they've taken the cylinder and they've kept it in the transverse way, put the cylinder in it, and they've projected. Now, some of the things that we need to note for this system is that there's 60 zones divided at 6 degrees wide, and it has false easting even when negative. And finally, y is set to zero, set at the south pole or the equator. So finally, this is what you have. So you have the whole Earth projected on this system, divided by 60 zones from here all the way here, and you have this whole sphere on this flat surface. The UTM system is widely used. It's a projected system that I'm sure a lot of us have seen in different on in different planning stages or parts of our operations. Another very important one, like I said, because I have used this system a lot, where we've had wells. Now this is Nigeria, and this is a system used most times in Nigeria. Now this system was developed, I think it was from the Clark 1888, if I'm correct, and sorry, it referenced the Clark 1888, if I'm correct, and sorry, Clark 1880 is actually written here. So it's based on the transverse Mercator system, and it references the Clark 1880, and the datum system is called the two things in Nigeria is called the Mina datum, and it's divided pretty much into three zones. So you have the west belt, you have the mid belt, and you have the east belt. And so what it means that any wells that you'll be drilling at this part of the system, or rather this part of the country, you will be referencing the west belt. If the wells are towards this region, you will be referencing the mid belt, and if they are towards this area, you'll be referencing the east belt. So I take us back to our very important question to differentiate between these three systems, the three datum systems. And perhaps now we'll be trying to answer these questions, and we'll just go straight. So the first one, WGS 84, if you can remember clearly, we said if it doesn't have an alphabet at the end, it is a horizontal datum system. So it's the World Geodetic System of 1984. It is a horizontal datum system. The next one, the WGS 84E, is a vertical datum system. It's the World Geodetic System, created the same year, but it's a vertical system because it references, and this one references the ellipsoid. Then finally, the last one, the WGS 84G, the G at the end telling us that it references the geoid, and it's a vertical It's a vertical system. So these are some of the references, some of the places I got some of the information used to prepare this information, and just so that we know, this is what the second book looks like. This is datum and map projections for remote sensing and GIS surveying. Sorry, let me bring that close to the camera. This is what the book looks like. So in case you're able to find it, it's a very decent book. And for this course or topic, just pay attention to chapters 1, 2, and 3, because that's where the book details quite a bit on these systems, especially the map projections on flat surfaces. So in summary, we have three types of projected systems. We have the global Cartesian coordinates, which references your x, y, and z. You have your geographic or your geodetic coordinates, where you use your longitude and latitude. Then finally, as drilling engineers, you need to have all this information on a flat surface, and they are now converted to what you call your northings and your eastings. It wasn't mentioned throughout the presentation. I just wanted to keep it simple, but just know that by the time you convert all this information on either the global Cartesian coordinates, or from the geographic geodetic coordinates, and put it on the flat system, it goes on from either longitude and latitude to become your northings and eastings, and put it on the flat surface. So if I want to tell you I am here on the flat surface, or you want to drill a well, and you make a reference using the northings and eastings, one just picks up that information, goes to that place, and is marked and pegged to commence drilling operations. So finally, thank you very much, everyone. Thank you for following us to the end of this topic. Thank you very much for listening. Please do not forget to go to our channel. There is a lot of resource with regards to drilling engineering, from well planning to bits, and we want to continue to build this database. Do not forget to go to the channel, watch. There are a lot of shorts that also summarize a lot of these topics, just in case you don't want to go into the main meat of the matter. Don't forget to like, don't forget to subscribe, and turn on the notification button, so you can always get a notification when we post new videos. Thank you very much, guys, and please do not forget to comment. We need your comments so that we can make this as interactive as possible. Thank you very much, guys, and see you on the next topic. Bye for now.